Now my dears, we go for question number 15. This question is very important from understanding point of view, purely theoretical discussion, no derivation, no mathematical formula. I just appeal everybody to take very special interest in the discussion, please. This question is about behavior of good conductor, that is metal, in external electric field. My dears, here in the textbook and in many other books, they have committed a slight mistake. They have written everywhere, instead of good conductor, they have written conductor. Now there lies my objection, because there are three types of conductors. One is poor conductor, another is semiconductor, third one is good conductor. Here they want to mean good conductor, that is metal. Okay? So as such they should have written good conductor or metal, because semiconductors are also conductors and poor conductors are also conductors. Better you say good conductor or metal. This is the clarification I wanted to make. Now onwards, if you find the word conductor in the textbook, you should understand good conductor, that is metal. Okay, fine. When you expose a metallic conductor against the external electric field, then how does it behave? What is its response? That is what we have to study. Come on. Let us study the whole theory in different three parts. First what we take? Solid conductor without cavity. Let me remind once again, conductor means here good conductor, that is metal. Okay. Consider solid conductor when subjected to external electric field. How will it behave? I am showing you. We have this sort of good conductor and it is solid. So I am putting such a inclined lines. This shading indicates it is a solid piece. Okay. The shape you can take any sort of shape, no problem. We just go according to textbook. Fine. Now on this metallic conductor, we apply external electric field. Suppose from left to right, this way. Okay, fine. The electric field lines of external electric field are shown here. Fine. Now what will happen? Look, these electric field lines are of external electric field. But now we are interested in finding out what happens inside the metallic conductor. Look, on the surface of this metallic conductor, the free electrons which have negative charge will experience electric forces in a direction opposite to external electric field. Don't you know, for a negative charge, it experiences electric force in a direction opposite to electric field. Right now, electric field is towards the right hand side, then electrons will experience electric forces towards left hand side. So from this part of the surface, electrons will start getting displaced towards left hand side. So they all will make displacement towards left hand side. Fine. So this part of the surface, after losing electrons, will become positively charged. Correct? That's why I am placing here plus signs. Okay? So positive charge is deposited on this part of the surface. But then those electrons will come at this end and they will be deposited here, making this part of the surface negatively charged. So I am putting minus sign. Fine. Now tell me, already you had applied one electric field, that is what we call external electric field, that was towards the right hand side, and that electric field towards the right hand side I have shown by symbol E dash, which is externally applied electric field. Okay. But now with the deposition of unlike charges on the opposite ends of this metallic conductor, there is a production of other electric field, and that is none but induced electric field. What is it? Induced electric field. That induced electric field is because of presence of unlike charges on the opposite ends. And what about direction of that induced electric field? From positive to negative. From positive to negative, this way, correct? And that induced electric field I have shown in the diagram with symbol E double dash. What was E dash? Applied electric field. What is E double dash? Induced electric field. But wait, they are in opposite directions. But what happens here? As more and more electrons transfer from right to left, what will happen? The strength of this electric field will go on increasing. At one stage, the magnitude of this electric field becomes exactly equal to magnitude of applied electric field. At that point of time, and then after, electrons stop getting displaced, because when these two electric fields which are inside this metallic conductor are of equal magnitude and opposite directions, will cancel the effect of each other, giving you resultant electric field to be 0, correct? So what happens when resultant electric field becomes 0? At that time, electrons on the surface, they simply get stopped at the respective positions, they no more displace, okay? When all the charges on the surface have come to rest, such a typical condition is known as electrostatic equilibrium condition. Electrostatic equilibrium condition. Okay, fine. Now, in this electrostatic equilibrium condition, some points are very interesting, quite noteworthy. You must remember them. Let us see one by one. In this electrostatic equilibrium condition, first point, the inside electric field has become 0. Inside electric field has become 0. Just now I explained. These two electric fields which are equal in magnitude, opposite in directions, will cancel the effect of each other, giving you resultant electric field inside the metallic conductor to be 0. Here I have written I for inside, I for inside, okay, fine. And then you just do one thing, consider this closed surface which is chosen very close to surface of the conductor, but inside the conductor, very close but inside the conductor, and this closed surface, you may call it Gaussian surface, does not have any charge enclosed inside, because inside this Gaussian surface you will find plenty number of neutral atoms, and when all the atoms are neutral, there is no charge, correct? Because whatever is the quantity of positive charge, same is the quantity of negative charge, there is no net amount of electric charge, correct? So inside this Gaussian surface, no charge is enclosed. So enclosed or inside charge is 0. Charge inside that Gaussian surface is 0, correct? Tell me, inside this Gaussian surface, when there is no charge, no electric field. No charge, no electric field, no electric field, no electric field lines, no electric field lines, then no electric flux linked with this Gaussian surface. So with this Gaussian surface, no electric flux is linked, and that's why I am writing here phi I equals to 0, correct? Fine. Inside this metallic conductor, there is no electric flux, phi I equals to 0. And last point, my dears, electric potential at every inside point is same, equal to whatever is the value of potential on the surface of that conductor. And tell me, last time also we had discussed this, whenever electric field is 0, there is no potential difference. No potential difference between any two points inside this conductor. No difference of potential means what? Potentials are equal. Potentials are equal. So at each point inside this conductor, potential is same, equal to whatever is the value of potential on the surface of the conductor, correct? So these are the special noteworthy points, and when these points come true, that condition is called electrostatic equilibrium condition. Electrostatic equilibrium condition. Okay. My dears, here this metallic conductor, whenever it is subjected to external electric field, it acquires electrostatic equilibrium condition almost at the same moment, because electrons simply transfer immediately, they take almost no time, and that is why this process is very fast. It is getting finished almost, you can say, instantaneously. Okay, fine. Now consider second possibility. We take that metallic conductor which has some cavity inside, that is some hollow part inside. You can see same figure I have drawn here, same figure, but what is the difference? Here the entire part inside was solid, no hollow part, and here we show this part as hollow, that is it has some cavity. Okay, fine. My dears, when such a metallic conductor having this sort of cavity is subjected to external electric field, as I explained in the previous section, it acquires electrostatic equilibrium condition instantaneously, very fast, and that is why I have written here E equal to 0. That is, inside this conductor, in this part where metal is present, there is no electric field. I am writing E equal to 0, correct? Like this only, here also there is no electric field inside this metallic conductor. Got it? Fine. But what about cavity? I am showing you. Look, for this cavity you can just do one thing, select one Gaussian surface inside the cavity, very close to the surface of cavity, but inside the cavity, not in the metallic conductor, okay, which is shown here with the purple color, and that Gaussian surface is this. Fine. Tell me, is there any charge enclosed by this purple colored Gaussian surface? No, there is no charge inside the cavity. No charge, then naturally no electric field. That's why I am writing E equal to 0. Correct? No electric field, no electric field lines, no linkage of any electric flux. Okay. So inside the cavity, no charge is enclosed, no electric field, no electric flux. Okay. And if you select Gaussian surface just outside the cavity, but inside the metallic conductor, then for this Gaussian surface also you can see it also does not enclose any charge, it also does not have any electric field, it also does not have any linkage of electric flux. Okay. These two Gaussian surfaces, this one and this one, they lie in the metallic conductor where electric field is 0. Inside the cavity also electric field is 0. Fine. Now, we take benefit of this physical situation in one problem, and that problem, that solution, that whole phenomenon is known as electrostatic shielding. Electrostatic shielding. Shielding means some protecting layer. Shielding means some protecting layer. Suppose you are out in the rainy season and it is likely to have some thunderstorm, likely to have some lightning. At that time, what you should prefer? You should prefer to remain inside your car. Okay? Inside the four-wheeler you are safe, you should close the doors and you should close the windows also. As long as you are inside the car, in a closed car, you are 100% safe. Though there may be any amount of lightning, no problem, because look here, consider this metallic conductor as metallic body of your car. So this is metallic body of the car and you are inside the car here in the cavity. Okay, and suppose there is lightning in the rainy season, and because of that lightning what will happen? external electric field will be applied on the body of the car. That external electric field applied on the body of the car will cause displacements of free electrons on the surface of the body, that is on the outermost layer, correct? Fine. So, on the surface there will be instantaneous displacements of free electrons, say from this side to this side. So, what will happen? This side of the surface, I mean this part of the surface will become positive and this part of the surface will become negative. But where you are present inside the cavity. Here there is no electric field, so you may touch anywhere here, no problem, because there is no electric field, you will not feel any electric shock, correct? Fine. But you should not dare to touch outside the car. You should not open the glass window. You should not dare to touch outside the car, that is on the external surface, because there is a charge on the outermost surface, correct? So, if you dare to touch over there, you will have some fatal electric shock and you will just invite your death. So, do not do that, okay? You are 100% safe inside the cavity. So, at that time tell me, there is a layer of electric charges on the outermost surface, that is called electrostatic shielding, which provides you necessary protection, okay? Come on. So, we take benefit of such a physical situation, okay? This whole phenomenon is known as electrostatic shielding, okay? Now, we go for third possibility. If there is some charge inside the cavity, here we had taken cavity, but we had not taken any charge inside the cavity. But now we take some amount of electric charge inside the cavity. Look, here is that cavity, inside which I am just putting some quantity of electric charge, say positive charge, and suppose 12 units. You can count the sign, plus signs, it will be 12, okay. So, plus 12 unit of electric charge I have just injected inside the cavity. Now, what will happen? I am showing you. Because of presence of this positive charge on the surface of cavity, negative charge will get induced with amount, same amount. Here plus signs are 12 and here you can count the number of negative signs, it is also 12. So, inducing charge is plus 12 unit and induced charge is minus 12 unit. Got it? Fine. Now, in this case, let us see where is electric field, where is no electric field. I am showing you. Consider this Gaussian surface, look here, this one, correct? Just inside the metallic conductor and very close to the surface. Very close to the surface, but inside the metallic conductor. For this surface, tell me, it does not have any net amount of electric charge contained inside, because the charge enclosed by this Gaussian surface is minus 12 plus 12, it is 0, no charge, no electric field, that is why I am writing E equal to 0, look E equal to 0, correct. You may consider this Gaussian surface which is inside the metallic conductor, but very close to the surface of cavity, correct. For that Gaussian surface also, net amount of electric charge is 0, because this is minus 12 and this is plus 12, again it is 0, correct. That is why here also I have written, come on, E equal to 0, fine. For such two Gaussian surfaces, E equal to 0. But what about inside the cavity? Consider this Gaussian surface inside the cavity. Now tell me, for this Gaussian surface, definitely it encloses some amount of charge, correct? And because it encloses some amount of charge, there is some electric field inside the cavity. That is why here I have written E is not 0. Electric field is not 0 inside the cavity, meaning thereby there is some electric field. And because there is some electric field, it will have some electric field lines also, and if it has electric field lines, naturally this electric field lines will associate with this Gaussian surface, and so this Gaussian surface will have some electric flux, correct. So, inside the cavity electric field is present, charge is enclosed, electric flux is linked, okay, fine. Have you noted one point common in all the three sections of the discussion? What is a common point? Whatever the physical situation may be, in every possibility, in every case, the electric field inside the metallic conductor is always 0. Whether you expose metallic conductor to external electric field or not, whether you keep some cavity inside the conductor or not, whether you keep some charge inside the cavity or not, irrespective of all these physical situations, every time it so happens there is no electric field inside the metallic conductor. So, this generalized fact you must remember, okay. In every case it so happens that electric field inside the good conductor, inside the metallic conductor is always 0, got it, fine. Now, we go for question number 16. It is about electric field on charged metallic surface. Consider some metallic conductor with any shape, but there is some charge on the surface of that conductor. Whenever you make any metallic conductor charged, it so happens that charge remains, that charge resides, it stays only on the outermost surface. It does not penetrate inside the conductor, okay. That is why I am putting all the plus signs on the outermost surface, correct, fine. So, here I am considering that metallic body which is already charged, correct. See, I am not applying any external electric field, I am not applying any external electric field, this body itself is having some charge, okay, fine. Now, for this charged body, how much is the strength of electric field at various points on the surface? That is what we have to find out. Look, just consider a very small cylindrical closed surface somewhere on the metallic conductor. Suppose I am taking it here. Consider this very small, very thin, narrow, closed cylinder, which normally we call pill box, correct. Pills means small tablets, and if you have box just to accommodate those pills inside, we call it pill box, correct. You must have seen the bottle for, box for Kushal Kanthil, it has this sort of cylindrical shape, okay, fine. Now, this is considered Gaussian surface which is closed and shape wise it is cylindrical. For this Gaussian surface, you can see this area and this area, they all are equal, correct. Let it be capital A, fine. Now, some charge is present on this area, which is the part of this metallic surface, correct. Let us find out that charge. Come on, in case of surface charge distribution, how would you find out charge? By formula, come on, surface charge density multiplied by area. Surface charge density I am taking sigma, this area is A. So, charge enclosed by this pill box here on this surface is Q equals to sigma A, correct. Now, tell me, because of presence of positive charge here, it will have electric field in the surrounding region. On the surface, that electric field I am showing this way, vector A outward, correct. Why outward? Why not inside? Because if you draw electric field vector here inside, it will be wrong from physics point of view, because this arrow would point inside the conductor, but just now I explained inside the metallic conductor there is no electric field. So, you must not show electric field vector inside. you must show it outside. Correct? Even if here presence of negative charges, then also electric field vector you must show outside, but not pointing this way away from the surface, you should point it this way towards the surface, but you must show that vector outside the metallic conductor. Okay, fine. Now, because this part is very small, almost you can say electric field at all such points on this very small part of the surface would be almost same. Let it be vector E, fine. So far this much extremely narrow surface is concerned, electric field you can take almost constant equal to vector capital E. And so far area vector is concerned, it is to be drawn always perpendicular to the area. Perpendicular to this surface element, that area vector you can draw this way. Again, for a closed surface you must show it outward. Okay, that's why I am putting vector dA this way. And in the direction of this vector E, I just take unit vector, say n hat. Now I am interested in finding out the magnitude of that electric field. Look, because there is a presence of charge, there would be electric field. If there is electric field, there would be electric field lines, and if there are electric field lines associated with this cylindrical pillbox, then it will have some linkage of electric flux. Let it be phi. And in chapter number 1, you were taught how would you find out electric flux linked with any surface? Just by finding surface integration of electric field over that surface. So surface integration of electric field will give you electric flux. Come on, for a closed surface, according to Gauss theorem, what is electric flux? It is charge enclosed by the closed surface divided by epsilon 0. Charge enclosed by this pillbox is this charge, and that charge we have taken small q divided by epsilon 0. Integration as it is, vector E dot vector dA means E into dA into cos theta. But here theta is angle between vector E and vector dA. Because they point in the same direction, angle theta would be 0 degree. This q upon epsilon 0 as it is. What about value of E? As I said just now, because this cylinder is very narrow, this area is very small, so that you can take electric field almost constant at all these points. Okay? If magnitude of electric field is constant, you can take it out of the symbol of integration, and then left is integration dA, correct? What is the value of Q? Value of Q is sigma into A. Q is sigma into A divided by epsilon 0. This E as it is. But what do you mean by integration dA? Integration dA means summation of areas of all the area elements chosen over given surface element. Come on. This surface element we have chosen here. Correct? In that also you can just choose extremely small surface elements, and then if you add up all those areas of all the surface elements, then it will give you this total area, and for this total area you know its value is capital A. So integration dA means summation of areas of all the surface elements taken over given surface, and that would give you this total area, which is right now capital A. So this part is capital A. Cancel capital A from both the sides, then you will get E equals to sigma upon epsilon 0. E equals to sigma upon epsilon 0. Correct? So this gives you magnitude of electric field on any point on the charged metallic surface. Correct? So from this formula we can see this value depends on the value of surface charge density. So if surface charge density at a typical point is more, then electric field will be stronger. At some other point on the same surface, if the surface charge density is less, then electric field will be weaker. Simple. Now what about vector E? You know vector equals to magnitude multiplied by unit vector. Magnitude of vector E is this much, sigma upon epsilon 0 multiplied by unit vector. Unit vector in the direction of vector E, we have taken n hat. That's why I am putting n hat. Correct? But suppose you are given negatively charged surface, then tell me, for negative charge surface, you will write vector E this way only, magnitude is sigma upon epsilon 0 only, but here you are supposed to write unit vector in the direction of this electric field. For a negative charge, direction of electric field will be pointing towards it this way. So it will have unit vector opposite to n hat. Opposite to n hat means minus n hat. So at that time here you can write minus n hat. Got it? Fine. This electric field on any part of the charged surface is found to be locally perpendicular. Locally perpendicular to the surface. Then you may have a question, why only perpendicular? Why not parallel? Why not tangential? I am showing you. Look. Suppose this is charged metallic surface. Look here. This one is charged metallic surface. Okay. If this is charged metallic surface, suppose positively charged, then I say electric field is normal to it. Normal means perpendicular. This way. But suppose you don't agree. Suppose. Then you should think of other direction. Suppose electric field is in this inclined direction. Suppose this way. Then such an electric field vector will have two mutually perpendicular components. One component you may think this way, another component you may think this way. Correct? Now tell me, this vector plus this vector plus this vector will make this vector. Okay? So this original E vector you can just decompose into two mutually perpendicular components, among which this one is parallel to this surface, we call it tangential component, and this one is perpendicular to the surface, we call it normal component. Okay. Now tell me, if this component is present, then what will it do? It will exert electric forces on the electrons, and then electrons have negative charge, so they will experience electric forces in the direction opposite to this electric field. That is, electrons will start getting displaced this way. But just now I said, once this metallic conductor is having deposition of electric charge on its surface, those all charges will remain steady at the respective positions. They do not move, they do not displace on the surface. Okay? So it means to say there is no force parallel to the surface. Why there is no force parallel to the surface on the charges? Because there is no electric field parallel to the surface. Now tell me, what is that vector which does not have parallel component? It must be perpendicular to the surface. So if total electric field is perpendicular to the surface, then it will have no tangential component. That's why no tangential force. That's why no movement parallel to the surface for the charges. Got it? Fine. So now onwards, remember, for any charged surface, the direction of electric field is always locally perpendicular. Locally perpendicular. And so for magnitude is concerned, magnitude is this much, sigma upon epsilon 0. So wherever surface charge density is more, electric field will be more. If surface charge density is less, electric field will be less. Okay? Fine. My dears, that's why in all these diagrams you can see I have shown some bending of this electric field lines. Why bending? Just to show that fact that electric field is perpendicular to the charged surface. Now this part of the surface is charged, and then all these angles must be 90 degree. You can see, if you bend this electric field line this way, then only this angle will be 90 degree. All these angles are 90 degree. Got it? Fine. That's why you need to draw this figure in this fashion. Okay? Fine. Come on, my dears. We proceed further. Question number 17 about capacitor and capacitance. Capacitor is sometimes known as condenser also, condenser, and capacitance is sometimes known as capacity. Now what do you mean by capacitor? What do you mean by its capacitance? Let us see. Capacitor is very important electric component to be used in electric circuit, whose job is to store energy in the form of electrostatic potential energy inside the electric field. That is its job. Okay. such an electric component which is called capacitor. How it is constructed? What is its capacitance? Let us see. Consider some metallic sphere supported by some non-conducting stand. Okay? You just do one thing. You start depositing more and more positive charge on its surface. Then naturally, the potential on the surface will go on increasing, because electric potential on the surface is K into Q upon R, that is K into charge upon radius. Correct? Naturally, when amount of charge on the surface increases, the value of electric potential on the surface will increase. Correct? What about electric field on the surface? Formula was from chapter number 1, KQ upon R square, that is K into charge upon radius square. K into charge upon radius square. Correct? Come on, can you rewrite this way? 1 upon R into KQ upon R. 1 upon R into KQ upon R. But KQ upon R is nothing but capital V. So this KQ upon R is capital V upon R. I mean to say, when you deposit more and more charge on this metallic sphere, this charge value will increase, then potential value will increase. When potential will increase, come on, electric field on the surface will go on increasing. Correct? But then, when that electric field reaches certain upper limit, after that, you know what happens? You cannot deposit any more charge. Why? I am showing you the reason for that. Once you start depositing charge on the surface more than a certain limit, then electric field on the surface crosses that upper limit, and then after it so happens that the constituent particles of surrounding medium start getting ionized. How? I am showing you. Look, suppose for this positive charge, you are talking about this part of the surface, then for a positive charge, don't you know, electric field is away from it. Electric field is this way. Fine. When electric field is this way, you can think of some atom of surrounding medium. That atom is electrically neutral. That atom is electrically neutral. But inside this electrically neutral atom, there are electrons. Electrons have negative charge. They will experience electric force in a direction opposite to electric field. If electric field is this way, then electric force will be this way. Correct? But if this electric field becomes sufficiently strong, then electrons are pulled out of this neutral atom, and then those electrons will be moving towards this charged surface this way. And after losing electron, this neutral atom will get transformed into positive ion. And that positive ion is repelled by this electric field this way. Electrons are attracted towards this positive charged surface. And then after this electron will simply neutralize this positive charge. Correct? So if this electron neutralizes this positive charge, then what will happen? The quantity of electric charge on this surface will go on decreasing, and that process is known as leakage of charge. Leakage of charge. So what I mean to say, when you try to deposit charge on the surface of the sphere more than a certain limit, then after the leakage will start and you cannot deposit any more charge. Correct? Fine. The maximum electric field applied on the surrounding medium till which its constituent particles do not get ionized is known as dielectric strength of the medium. Dielectric strength of the medium, it is nothing but maximum electric field. When charge is maximum, look here, when charge is maximum, naturally electric field will be maximum. So I am writing here E maximum, and here instead of Q I am writing Q maximum. Correct? That maximum electric field which can be applied on a given medium till which its constituent particles do not get ionized is known as dielectric strength of that medium. Dielectric strength of that medium. My dears, for air medium, the value of dielectric strength is 3000 volt upon millimeter. 3000 volt upon millimeter. Okay, fine. Now, here for this single component of the capacitor, you can see it has some ability, it has some capacity to store some amount of electric charge on its surface. Then such an electric component which has some capacity to store electric charge and ultimately electric field and ultimately electrostatic potential energy is only known as capacitor. An electric component which can store some electric charge, which can have some electric field in which some energy can be stored is known as capacitor. Okay? But in practice, we do not use that capacitor in which there is only one component. No. In practice, we use capacitor with two components. Now, why two components? I am showing you. Look. Consider this metallic sphere which has positive charge on its surface and separated electrical point of view by some non-conducting stand. Okay, fine. Now, what do we do to have more capacitance? What we do, I am showing you. We just bring another neutral sphere supported by non-conducting stand in the neighborhood of this first sphere. Correct? We just keep it quite close. There should not be any physical contact, but we should just keep it very close. Fine. Because it is kept very close, there will be induction of charge. Because of presence of positive charge here, electrons from this part of the surface will migrate this way and they will be deposited here. So, this part of the surface after losing electrons will become positive and this part of the surface after gaining electrons will become negative, but still it is electrically neutral. Here inducing charge is this and induced charge is this. You must show plus and minus sign with same number. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9. Here also count the number of negative signs 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Correct? Now this still has no net amount of electric charge. Minus 9 plus 9 will be 0. Okay. But now what we do? We want this component to have some net amount of negative charge, and for that sake what we do? We just connect this part which is positive to ground. We provide earthing. We provide earthing through this metallic wire. Fine. Now you know ground is also a good conductor. Then electrons from that ground, from that earth surface will just migrate this way towards this higher potential part, towards this positively charged part. Okay? And if electrons migrate this way, they will just neutralize this positive charge. Fine. After this positive charge is neutralized, then after you should cut this wire. Correct? And then tell me, if you cut this wire, this negative charge will get spread uniformly over the entire surface, and you can see here you have one more component which has negative charge, say minus capital Q. This has positive charge plus capital Q, this has negative charge minus capital Q. Now here, compared to this capacitor having only one component, compared to that, this capacitor having two components has ability to store more amount of electric charge. It can have stronger electric field on its surface without causing any breakdown of surrounding medium, without causing any ionization of the surrounding medium. So such a system now onwards we will regard as a capacitor. How would you define it? A system made up of two conductors placed near to each other but separated from each other, having arbitrary shape and volume but having equal amount of opposite charges is known as capacitor. So such a system now onwards we will regard as a capacitor. The shape of the components, at present we have shown spherical shape, but normally in practice we use that sort of capacitor which has the components in the form of parallel plates. That is why we call it parallel plate capacitor, parallel plate capacitor. Now onwards in the entire chapter, we will talk about only parallel plate capacitors. Okay? Now let us see what do you mean by capacitance of a capacitor. The ability of a given capacitor to store electric charge is measured by one physical quantity called capacitance. Measure of ability of given capacitor to store electric charge is given by one physical quantity called capacitance, and it is shown by symbol capital C. How do we define it? Very simple. We define it by such a ratio Q over V. Q over V. What is Q? It is magnitude of charge on either conductor of a capacitor, and V is the potential difference between two conductors in a capacitor. Okay? Normally we do not call conductors, we call plates. So this is the magnitude of charge on either plate, and this is the potential difference between two plates of a capacitor. Now using this ratio you can define capacitance this way. For a given capacitor, the ratio of magnitude of electric charge on either of the two plates in that capacitor and potential difference between those two plates is called capacitance of that capacitor, shown by symbol capital C. How do we define this capacitance? Very simple. Ratio of magnitude of electric charge on either plate of a given capacitor to potential difference between two plates in that capacitor is called its capacitance, shown by symbol capital C. Once again, ratio of magnitude of charge on either plate of a capacitor to the potential difference between two plates in that capacitor is called its capacitance, shown by symbol capital C. Right? Now, compared to this capacitor having only one plate or one component, how does this have greater capacitance? I am showing you. Suppose this negatively charged sphere is not present, suppose, and then you have only one component having positive charge. In that case, suppose electric potential here is say 10 volt. At this very point electric potential is suppose 10 volt, and if you bring another negatively charged sphere in the neighborhood, then due to the presence of negative charge, here at the same point you will have some negative value of the potential, let it be minus 4 volt. So ultimately what will be the total potential here? It will be 10 plus minus 4, that is 6 volt, correct? So in this situation what happens? That the potential difference between these two, that goes on decreasing, correct? Here in this case, because this potential decreases, then capacitance would increase. When potential will decrease, look here, when potential difference will decrease, electric field on the surface will also decrease, and if electric field on the surface decreases for the same amount of charge, earlier it was causing breakdown of the surrounding medium, but now same amount of electric charge produces weaker electric field in the surrounding region. So now you have a chance to increase the electric field further till it reaches the limit of dielectric strength, correct? So in that process you can still deposit some extra amount of electric charge, so it has enhanced capacitance, enhanced, that is increased capacitance, correct? So this is the benefit of using a capacitor having two components, having two plates, got it? What about SI unit of capacitance? SI unit of capacitance is given in the memory of scientist Mr. Michael Faraday. The SI unit of capacitance is farad. How do we write it? Farad, F-A-R-A-D, but starting with small f. When you are referring name of Faraday as a name of person, you may start the spelling with capital F, but here we are referring farad with for the SI unit of capacitance, not for the name of a person. Okay. So, you must start with small f. Okay. Farad is the SI unit of capacitance, but from this formula, here when you write Farad, here also you must write SI unit. What is SI unit of charge? Coulomb. SI unit of potential difference is volt. So, Farad equals to Coulomb upon volt. Farad equals to Coulomb upon volt. Okay, fine. In practice, we find this Farad unit quite big, very large. In practice, we have very small values of capacitance as compared to Farad, and that is why we just prefer to use very small units, say microfarad and picofarad. 1 microfarad, it is 10 raised to minus 6 farad, 1 picofarad is 10 raised to minus 12 farad. I hope you must have remembered the table of submultiples, that is power, negative power to the base 10. Remember this table of submultiples starting with 10 raised to minus 1. Come on, speak out. Deci, centi, milli, micro, nano, pico, femto, etto, zepto, yocto. Remembered? Deci, centi, milli, micro, nano, pico, femto, etto, zepto, yocto. And in that, micro means 10 raised to minus 6 and pico means 10 raised to minus 12. Correct? Fine. What is the circuit symbol for showing the presence of parallel plate capacitor in the circuit? It is this symbol for that capacitor which has fixed value of capacitance. Okay? But if capacitance of a capacitor is variable, then you can just show it by such a circuit symbol, in which you have to add one more arrow. Okay? This is the circuit symbol of a capacitor having fixed value of capacitance. This is the circuit symbol for that capacitor which has variable value of capacitance. Got it? How would you define 1 farad capacitance? 1 farad capacitance. Very simple. If you want this value to be 1 farad, you should take this both the values 1, so that this ratio will come out to be 1, but that too in SI unit. If you take Q equal to 1 coulomb, V equals to 1 volt, then 1 upon 1, that is 1 coulomb upon volt. But coulomb upon volt is nothing but farad. Correct? If magnitude of charge on either plate of a given capacitor is 1 coulomb, and at the same time the electric potential difference between two plates of that capacitor is 1 volt, then its capacitance is said to be 1 farad. Last time, if magnitude of charge on either plate of a given capacitor is 1 coulomb, and at the same time the value of potential difference between two plates of that capacitor is 1 volt, then its capacitance is said to be 1 farad. Simple.